All right, so I'm just showing you here kind of two different notations, right? So here is the Python notation. Oops, sorry. And here is the ACL2 notation, right? And again, this notation here, what we're really doing is finding what row am I in, right? And those are in the definition by cases. Okay, this one is more of a how do I find the answer. So this is a what is the answer. And this is a how do I find the answer. That's the distinction. This is called imperative. Okay, imperative means you give commands. How do you do it? Do this, do that. Okay, and this is called the functional approach. Okay, and the functional approach is define a function that does it, right? Don't think in terms of commands to compute the function. Think in terms of what the function is. Okay, so that's just two different notations. You get used to whatever notation you program most in. Okay, and but one thing that I'm going to make a distinction here is because this is a course in discrete math, right? We're doing a lot of proofs, so I want you to think about the fact that programs are actually discrete structures, okay? And we can prove properties about them. Like, for example, remember I showed you those two different definitions of maximum? One that thought in terms of the maximum of the rest of the list, and one that thought in terms of finding the maximum of the first two elements, right? It would be nice to be able to show that those two always give the same results, right? So yeah, that would be nice, okay? But if you try to do any proofs at all in a language like Python or Java or C++, what you end up having to think about is time. So you reason like this: after k times through the loop, this is the value that m has, okay? And then argue that at the end of the loop, right, then m now has to have something like m has maximum of all elements. Trying to figure out what m has like the maximum of the first k elements, right? That's actually a difficult thing to do. There's the term for this. What this is known as a loop invariant, okay? And finding loop invariants, and a loop invariant is just how to describe what the loop is doing at any point. It's actually very, very difficult, okay? And like I said, that's what you need to be able to do so that you can say, oh, and at the end, then this is what it has, okay? So that's why it's actually difficult to prove things about languages like Python and C++, but it's a lot easier to think about the functional case, because in the functional case, you have this function is equal to that, right? F of x is equal to that. The maximum of our list is equal to this. And then all of the machinery that we developed in this course actually works, okay? So that's why in this course we really only deal with functional languages. Now here is the two different syntaxes for defining equations, okay? So this is what we call the defining equation, and this is kind of the logic axioms way. And this is kind of the by cases way, okay? Either way is fine, okay? The only thing I'll say is that this is using patterns on the left-hand side of the equality. And this is what I mean, right? That is a pattern, okay? This is using a simple variable on the left-hand side and conditions or cases on value of that variable. Okay, so here are my cases. If x is equal to this, if x is equal to that, if x is equal to that, and so on, right? This is kind of the ACL2 style, and this is the ML style, okay? So what that means for you is that you really should try to become comfortable with both styles, okay? They both have their uses. In this class, we're going to be using the ACL2 style exclusively, right? So we're going to use this a lot, and so you should become very comfortable defining functions that way. In, say, the functional programming course, right, then you'll use DML style, because that's the language that's used there. Okay, so I do want to go back to this idea and kind of emphasize this a couple of points, and that is that thinking about variables that change over time is really hard. Okay, that is honestly hard to do formally. Okay, because not only do you have to think about values, you also have to think about time. Okay, to make that work. Okay, and when there's more than one thing happening at a time, then it becomes absolutely painful, because okay, so x right now has this value. And so now, because x has this value, that means that this new expression that uses x has that value. But how do you know that x didn't change between those two statements? It could be that some other thread is changing x, right? And when does that happen? You know what? That's going to happen in any kind of a web setting, okay? Because when you have a web setting, there might be two people looking into the web page at the same time, right? When you have a mobile application, again, the mobile application needs to have lots of things going on at once so that the phone doesn't get bogged down, right? Oh, I'm sorry. I'm not actually right now listening to incoming phone calls because you're in the middle of writing a text. No, it has to keep doing many things at once, right? Same goes for a desktop application. The desktop application, it can't say, oh, I am not going to respond to any mouse clicks because I'm in the process of saving a file. You'd hate that, right? The thing gets unresponsive. And if you have a server-side application, like for example, a web server, right? Then it can't just assume that there's only one web page being served at a time. There's lots of requests coming in, okay? Now, if you want to run on a multi-core system, and I bet you money that your laptop or your favorite computer is a multi-core system, right? Or God help us, a GPU system, a graphics system, right? So if that's happening, then yeah, there's lots of things going on at the same time, right? So it makes it very, very difficult to reason about the value of things, right? So that's really hard. And I'm giving you a heads up. In the future, we might have to make software guarantees. What does that mean? It means we might have to be able to write a contract that says that a software does the following in any circumstance. And imagine, for example, that you're writing software for the brake handling mechanism of a car, right? You can't just kind of say, oops, I'm sorry. It was in the middle of doing something else, so it stopped monitoring the tire rotation. No. It can't do that, right? That might actually be a contract. It might actually be a government regulation that says this stuff needs to have a high degree of assurance. So we have to get a little less cavalier about writing software and throwing it out there. We may have to prove some properties, and that's really tough to do for imperative style programming. Okay, so that's the reason that a lot of frameworks are actually going back to the functional. And I say going back because we invented functional programming in the late 1950s. Okay, so it's making a huge comeback here. All right. For example, Scala, I mentioned, that's a functional language. If you go to the web, you can Google something called reactive programming. This is like the latest thing going on in web programming, and it's actually a functional style of programming, right? And the reason is that it's easier to argue informally, right? Or prove, if you want to be formal, that your program actually does what it's supposed to do. So keep that in mind. I mean, functional programming is something that's actually really important and forward-looking. So I want you to really respect that.